The thermometer hanging on the porch of Elias Drummond's cabin read 12 degrees below zero. It was February of 1887, deep winter in the Sawtooth Mountains of Idaho Territory, and the kind of cold that made every breath visible, every movement painful. Inside every other cabin scattered through the mining camps and trap lines, men huddled close to their stoves, feeding fires constantly, burning through wood at an alarming rate while still shivering in their coats. Cabin temperatures hovered around 30 to 35 degrees on a good day, barely enough to keep water from freezing. But inside Elias Drummond's cabin, something impossible was happening. The mercury showed 40 degrees Fahrenheit. 40 degrees. The kind of temperature where a man could work in his shirt sleeves, where water stayed liquid, where comfort was actually achievable. That's a 52-degree difference from outside. 52 degrees warmer with a fire that looked like it was burning backwards, upside down, completely wrong in every way that mattered to conventional wisdom. Elias's neighbors had warned him. They'd said his stove design was insane, that fires don't burn from the top down, that he'd fill his cabin with smoke and die of poisoning. They'd predicted failure within days of his first firing. That was 4 months ago. Elias was not only alive, he was warmer than anyone else in a 100-mile radius. When a trapper named William Corbin finally made the trek to Elias's cabin in mid-February, struggling through hip-deep snow and fighting wind that cut through every layer of clothing, he expected to find Elias either dead or having abandoned his foolish experiment. Instead, he found Elias comfortable in his shirt sleeves, reading a book by lamplight, with a fire that was burning in a way that seemed to violate the laws of nature. The fire was at the top of the fuel load. The flames burned downward through the wood rather than upward. Smoke somehow managed to exit properly, despite this backwards combustion. And the cabin was warmer than Corbin's cabin had been at any point all winter. "Elias," Corbin said, his voice hoarse from breathing cold air for hours, "your stove is upside down. The fire is at the top. Fire doesn't burn down. It burns up. You've built this wrong." Elias looked up from his book and smiled. "The stove is built exactly right. What you think is upside down is actually the most efficient way to burn wood that exists. Top-down combustion. The wood burns from the top layer down to the bottom. Every other stove in Idaho burns from bottom up and wastes most of its heat. Mine burns top-down and wastes almost nothing. That's why I'm warm and you're freezing." Corbin moved closer to the stove, examining it carefully. The fuel chamber was loaded with split wood, stacked in neat layers. The top layer was actively burning, flames consuming the wood and creating a bed of coals that was gradually working its way down through the stack. Below the burning layer, the wood was being preheated by the heat from above, driving out moisture and volatile gases. These gases rose up through the burning layer, where they ignited and burned completely, adding to the heat output. It was a controlled, cascading burn that moved methodically from top to bottom. "But you're going to run out of fire," Corbin protested. "When the flames burn through the top layer, they'll go out." "There's nothing above to keep them going." Elias shook his head. "When the top layer burns through and becomes coals, those coals ignite the layer below. The process continues until all the wood is consumed. I load the stove once every 18 to 20 hours. One loading. No tending in between. The fire manages itself. Your stove requires feeding every 2 to 3 hours, or it goes out. Which design is actually wrong?" Corbin had no answer. He stood in the warm cabin, watching a fire burn in a way he'd never seen before, and realized that everything he thought he knew about heating might be mistaken. What Elias Drummond had built was a stove that everyone said couldn't work, shouldn't work, and would kill him if he tried to make it work. But it did work. It worked so well that it kept his cabin 52 degrees warmer than outside while using 1/4 the wood his neighbors consumed. The story of how he designed it, why it functioned so efficiently, and why everyone was convinced it would fail reveals fundamental truths about combustion, heat transfer, and the difference between doing things the way they've always been done and doing things the way they should be done. Elias Drummond was not a typical mountain man. Born in Connecticut in 1852, he'd studied engineering at Yale before financial problems forced him to leave after 2 years. He'd worked various technical jobs, machine shops, foundries, a brief stint with a railroad, before heading west in 1878 at age 26. He'd tried mining, tried logging, and finally settled into trapping in the Sawtooth Mountains, but his engineering education had given him something most trappers lacked: a systematic way of analyzing problems and designing solutions based on first principles rather than tradition. When Elias built his cabin in the summer of 1886, he knew that the standard approach to heating, a cast iron stove burning wood from the bottom up with constant feeding, was grossly inefficient. He'd calculated that conventional wood stoves converted only 15 to 25% of the wood's energy into useful heat. The rest went up the chimney as hot exhaust, unburned gases, and wasted potential. This bothered him, not just because it wasted wood and required constant labor, but because it was intellectually offensive. The laws of thermodynamics said you should be able to extract far more energy from wood if you burned it properly. The question was how. Elias spent the fall of 1886 studying combustion theory and experimenting with different burning methods. He learned that wood combustion happens in stages. First, heat drives moisture out of the wood. This requires energy but produces no useful heat. Second, heat drives out volatile gases, the organic compounds that make up about 70% of wood's energy content. Third, the remaining char, essentially carbon, burns directly in contact with oxygen. In a conventional stove, wood is added at the bottom, flames rise up, and hot exhaust escapes through the chimney. Much of the volatile gas released from the wood doesn't burn completely because it doesn't spend enough time in the hot zone. These unburned volatiles escape up the chimney, carrying energy away. The wood at the top of the fuel load, farthest from the initial flame, releases its moisture and volatiles slowly, inefficiently, creating smoke and creosote. Elias realized that if he could invert the process, burning from the top down instead of bottom up, he could solve multiple problems simultaneously. Top-down combustion would preheat the fuel below the burn zone, driving out moisture and volatiles in a controlled manner. Those volatiles would rise up through the active flame zone, where they'd burn completely at high temperature. The char left behind would form a bed of coals that would ignite the next layer down. The process would be self-sustaining, self-feeding, and far more efficient than conventional bottom-up burning. The challenge was designing a stove that would enable and sustain this inverted combustion. In October 1886, Elias began building. The stove he constructed looked bizarre to anyone familiar with conventional designs. The firebox was a vertical chamber, approximately 16 inches square and 36 inches tall, much taller and narrower than a typical horizontal firebox. At the bottom of this chamber was a grate, but unlike conventional grates that supported burning wood, this grate supported unburned wood. At the very top of the chamber, Elias built a loading door where fuel would be added. Below this door, he installed what he called the ignition shelf, a heat-resistant steel plate that could be pulled out like a drawer. On this shelf, he would place kindling and small wood to start the fire. Once the fire was established on this top shelf, he'd push the shelf back in, sealing the top of the chamber except for the exhaust outlet. Below the ignition shelf, he'd load the main fuel, split wood stacked in layers, each layer perpendicular to the one below it for stability. The wood would fill the chamber from just below the ignition shelf down to the grate. When he lit the fire on the ignition shelf and pushed it back into position, the flames would burn the kindling and begin igniting the top layer of main fuel. As that top layer burned, it would create coals that would drop slightly and ignite the layer below. The process would continue layer by layer until all fuel was consumed. The exhaust system was equally unconventional. Instead of a chimney exiting from the top of the firebox like a normal stove, Elias's exhaust exited from the side, about 2/3 of the way up the vertical chamber. This meant exhaust gases had to rise from the burning layer at the top, contact the wood stacked below. transfer some heat, then exit through the side port. This heat transfer dried and preheated the unburned wood, making combustion more efficient when that wood's turn came to burn. From the side exhaust port, the pipe ran horizontally for 8 feet, jacketed in a secondary pipe that created a heat exchanger similar to Martin Vogel's design. Hot exhaust heated the airspace between pipes, and that heated air vented into the cabin. After 8 feet, the exhaust turned upward and exited through the roof. This long path extracted maximum heat before the exhaust escaped. Air intake was controlled by a single adjustable vent at the very bottom of the firebox. This vent fed oxygen to the burning coals and created a gentle updraft through the fuel stack. The key was balance. Too much air and the fire would burn too fast, consuming fuel rapidly without extracting full heat. Too little air and combustion would be incomplete, producing smoke and carbon monoxide. Elias calculated the optimal vent size based on estimated fuel load and burning rate. He could adjust it if needed, but the goal was to set it once and let the system self-regulate. When Elias showed his design to his few neighbors in October 1886, the response was universally negative. A miner named Jack Sutherland examined the stove and shook his head. "This is backwards. Fire burns up, Elias. Everyone knows this. You can't make it burn down. It's not natural." Elias, patient as always, tried to explain. Fire burns wherever there is fuel, oxygen, and sufficient heat. In this stove, the top layer of wood has all three. As it burns, it creates heat that ignites the layer below. The direction is downward because that's how I've designed the fuel loading. Sutherland remained unconvinced. "Even if it works once, you'll have to reload after every burn. My stove, I just add a log to the fire whenever it gets low. Yours, you have to let the whole thing burn out, then reload from scratch. That's less convenient, not more." Elias nodded. "True, I must reload completely each time, but I reload once every 20 hours. You add wood every 2 hours. Over 20 hours, you've handled wood 10 times. I've handled it once. Which is more convenient?" Sutherland had no counter-argument but remained skeptical. The real test, everyone agreed, would come when Elias actually fired the stove. That test came in early November 1886. Elias loaded the firebox with split pine, well-seasoned and dry. He stacked it carefully in 8 layers, each layer 3 pieces of wood arranged perpendicular to the layer below. The stack rose from the grate to just below the ignition shelf. On the ignition shelf, he placed kindling and very small splits. He adjusted the bottom air vent to his calculated setting. Then he lit the kindling. The kindling caught immediately and burned hot. Flames rose to the top of the chamber and began licking at the ceiling of the firebox. Elias pushed the ignition shelf back into position. The flames continued burning, now consuming the kindling and beginning to ignite the top layer of main fuel. Over the next 30 minutes, the top layer caught fire fully. Flames consumed the 3 pieces of wood, creating intense heat and a growing bed of coals. The coals settled downward, contacting the second layer of wood. The heat from the coals and flames dried this wood, drove out volatiles, and ignited it. The process continued. Layer by layer, the fire moved downward through the fuel stack. Each layer burned for approximately 2 to 2.5 hours. 8 layers meant the full fuel load would burn for 16 to 20 hours before needing replacement. The exhaust coming out of the side port was hot, probably 600 to 700 degrees initially, but it was remarkably clean, very little visible smoke. The volatiles were burning completely in the hot flame zone at the top of the fuel stack. What little smoke formed was being consumed by the intense heat. The cabin air remained clear and breathable. No smoke, no fumes, no smell of incomplete combustion. The heat output was steady and controlled. Unlike conventional stoves where heat output spiked when wood was added and declined as it burned down, Elias's top-down design provided remarkably consistent heat. Each layer burned at approximately the same rate with approximately the same heat output. The cabin warmed quickly. Within 2 hours, the interior temperature reached 55 degrees. Within 4 hours, 60 degrees. By evening, the cabin was at 65 degrees, while outside temperature was 25 degrees, a 40-degree differential with a fire that had been lit once and not tended at all since ignition. Elias monitored the system carefully for the first week. He recorded temperatures, burn rates, wood consumption, and any operational issues. The data was impressive. Fuel load of approximately 30 pounds of wood burned for 18 hours. Heat output averaged around 8,000 BTUs per hour. Cabin temperature maintained at 60 to 65 degrees, with outside temperatures ranging from 15 to 30 degrees. Wood consumption was approximately 40 pounds per day, or 1.6 pounds per hour. A conventional stove achieving similar heat output would consume 6 to 8 pounds per hour. Elias's efficiency advantage was 4 to 5 times better. When Jack Sutherland visited a week after the first firing, he found Elias comfortable, warm, and emphatic about the system's performance. "It works better than I calculated," Elias said. "The thermal efficiency is at least 60%, maybe higher. Conventional stoves are 15 to 25%. At best, I'm extracting 3 times more useful heat from the same amount of wood." Sutherland examined the stove. The fire was burning steadily about halfway down the fuel stack. The top half of the stack had been consumed. The bottom half waited its turn. The process was orderly, controlled, and self-sustaining. Despite his initial skepticism, Sutherland had to admit it worked. But he still had concerns. What happens if the fire goes out before the full load is consumed? You've got half-burned wood sitting there. You can't just light it from the top again. Elias acknowledged this was a potential issue. If combustion failed partway through, restarting would be difficult. But in his testing so far, the fire had never gone out prematurely. The system was inherently stable. As long as the air vent was set correctly and the wood was dry, combustion proceeded reliably from top to bottom. Still, Sutherland and others remained dubious. An upside-down fire seemed like a clever trick that might work in ideal conditions, but would fail when stressed. Winter would provide that stress. The winter of 1886 to 1887 proved to be severe. By December, temperatures regularly dropped below zero. By January, sustained cold of 10 to 20 below became normal. Conventional stoves struggled. Men burned wood at unsustainable rates, depleting their supplies and exhausting themselves cutting more. Cabins stayed barely above freezing despite constant effort. Elias's cabin remained at 40 to 45 degrees, even in the coldest weather. The upside-down stove burned steadily, one load every 18 to 20 hours, providing consistent heat without constant tending. The difference between 40 degrees and 30 degrees might not seem enormous, but it's the difference between comfort and misery, between sleeping soundly and waking up shivering, between working productively and just trying to survive. Elias's quality of life was categorically better than his neighbors. When February brought the worst cold of the winter, 12 below zero for days on end, Elias's cabin reached its peak performance. 40 degrees inside, 52 degrees warmer than outside, one fuel loading every 20 hours, perhaps 35 to 40 pounds of wood per day. His neighbors were burning 150 to 200 pounds per day and achieving 30 to 35 degree interiors. Elias was using 1/4 the wood and achieving 10 to 15 degrees more warmth. The efficiency advantage was overwhelming and undeniable. William Corbin's visit in mid-February, when he found Elias warm and comfortable with his upside-down fire, marked the turning point. Corbin was a practical man who respected results over theory. He asked Elias to teach him how to build a similar stove. Elias agreed. That spring and summer of 1887, Elias built 3 upside-down stoves for neighbors. Each installation was customized to the specific cabin size and heating needs. Some were smaller for one-room cabins. Others were larger for families. But the core principle remained the same: vertical firebox, top-down combustion, extended heat extraction through exhaust heat exchangers, minimal tending required. The following winter, 1887 to 1888, the results were consistent across all installations. Dramatic fuel savings, 40 to 60% less wood consumed compared to conventional stoves. Higher cabin temperatures, typically 5 to 15 degrees warmer. Reduced labor, 1 loading per day instead of 10 to 12 feeding cycles. Cleaner combustion, less creosote, less smoke, better air quality. Every measurable metric favored the upside-down design. Word spread through the trapping and mining communities. The crazy upside-down stove actually worked better than normal stoves. People began seeking out Elias for advice and construction help. If this story of forgotten heating innovations is teaching you principles that could still apply today, please take a moment to subscribe to this channel. Hit that subscribe button and turn on notifications. We explore historical techniques that solved problems with elegant engineering, knowledge that's been forgotten but shouldn't be. Your subscription helps us continue this work. Now let's dive into the science of why Elias's upside-down stove worked so spectacularly well. The physics of top-down combustion, what Elias called his upside-down burning method, operates on principles that modern combustion engineers would recognize as staged combustion and controlled pyrolysis. First, the concept of wood combustion stages. Wood doesn't burn directly. It decomposes through heat in a process called pyrolysis. Below approximately 200 degrees Fahrenheit, wood is stable. Between 200 and 500 degrees, moisture evaporates. This is endothermic, absorbing energy without producing useful heat. Between 500 and 900 degrees, pyrolysis occurs. Complex organic molecules in the wood break down into simpler volatile gases, including carbon monoxide, hydrogen, methane, and many others. These volatiles contain approximately 70% of the wood's total energy. Above 900 degrees, the remaining char, which is mostly carbon, oxidizes directly, producing carbon dioxide and heat. In a conventional bottom-up fire, all three processes happen simultaneously in a chaotic mixture. Wood at the bottom is fully burning. Wood in the middle is pyrolyzing. Wood at the top is just beginning to dry. The volatiles released from partially heated wood rise up and often escape without fully burning because they don't pass through a hot enough zone. This incomplete combustion wastes energy and creates smoke. In Elias's top-down design, the stages happen sequentially and completely. The burning layer at the top creates intense heat, above 1,000 degrees in the flame zone. Wood directly below this burning layer is heated to pyrolysis temperature. Volatiles are released and immediately rise up into the 1,000-degree flame zone where they burn completely. The heat from complete volatile combustion adds to the overall energy output. Meanwhile, wood further down the stack is being gently preheated by heat radiating downward and by warm exhaust gases. This preheating drives out moisture gradually, without wasting energy. By the time each layer reaches the burning zone, it's fully dry and ready for efficient combustion. The result is staged combustion. Drying happens first, pyrolysis happens second, char burning happens third. Each stage is optimized, unlike conventional fires, where all stages happen simultaneously and interfere with each other. This staging explains why Elias's stove achieved 60% efficiency, while conventional stoves achieved 20%. More of the wood's energy was converted to useful heat rather than wasted in incomplete combustion or in evaporating moisture. Second, the principle of complete volatile combustion. As mentioned, volatiles contain 70% of wood's energy. Ensuring complete volatile burning is critical for efficiency. In conventional stoves, volatiles released near the firebox walls or from wood at the edges of the fuel load often don't reach the hot flame zone. They condense into creosote or escape as smoke. In Elias's design, all volatiles released from the layer being pyrolyzed must rise through the active flame layer above. This guarantees they pass through temperatures sufficient for complete combustion. The tall, narrow firebox design forced volatiles to travel upward through the hottest part of the fire. Modern high-efficiency wood stoves use secondary combustion chambers that re-burn volatiles. Elias achieved similar results with his top-down geometry. Third, the heat transfer to unburned fuel. Preheating fuel before combustion improves efficiency by reducing the energy needed to bring wood to ignition temperature. Elias's design heated the fuel below the burn zone through radiation, conduction through the stack, and contact with warm exhaust gases. By the time wood reached the burning layer, it might already be at 400 to 500 degrees, significantly reducing the energy needed to ignite it. This preheating effect is why each layer ignited readily from the coals of the layer above. No additional kindling or fire starting was needed after the initial ignition at the top. Fourth, the controlled combustion rate. The narrow firebox and limited air inlet at the bottom created natural flow restrictions that prevented the fire from burning too rapidly. In a conventional stove with large air openings, fire can burn uncontrollably fast, consuming fuel rapidly but extracting heat poorly. Elias's restricted air supply forced slow, controlled burning that maximized heat extraction time. The burn rate was approximately 1.5 to 2 hours per layer. This slow rate gave time for complete combustion and full heat transfer. Fifth, the exhaust heat recovery. The 8-foot horizontal heat exchanger section captured heat that would otherwise escape up the chimney. Hot exhaust at 600 degrees entered the heat exchanger and exited at 300 degrees. 300 degrees of heat transferred to cabin air. This captured approximately 50% of the heat in the exhaust, effectively doubling the useful heat output compared to a straight chimney. Modern condensing furnaces use similar principles, extracting so much heat that water vapor condenses. Elias's system didn't quite reach condensation, but it captured a large fraction of exhaust heat. The mathematics of the efficiency improvement are straightforward. Wood contains approximately 8,000 BTUs per pound when completely burned. Elias's stove consumed approximately 1.6 pounds per hour and produced 8,000 BTUs per hour of useful heat. Efficiency equals useful heat divided by fuel energy equals 8,000 divided by 1.6 times 8,000 equals 8,000 divided by 12,800 equals approximately 62%. A conventional stove producing 8,000 BTUs per hour might consume 6 pounds per hour. Efficiency equals 8,000 divided by 48,000 equals approximately 17%. Elias's system is 3.6 times more efficient. This efficiency difference explains the 52-degree temperature advantage. With the same heat loss rate from the cabin, achieving higher interior temperature requires higher heat input, but Elias achieved higher temperature with lower fuel input because his efficiency was so much better. The fuel savings were dramatic. Over a 6-month winter, Elias burned approximately 7,000 pounds of wood, about 3.5 tons. His neighbors burned 20 to 25,000 pounds, 10 to 12 tons. Elias saved 7 to 8 tons of wood. At approximately 1 day of labor per cord, and a cord being roughly 2,000 pounds, Elias saved roughly 7 to 8 days of labor over the winter. Every winter. For as long as the stove lasted, the safety concerns that neighbors initially raised about the upside-down design were not unfounded in principle but were overcome by proper implementation. The concern about carbon monoxide production from incomplete combustion was valid, but Elias's design promoted complete combustion through high temperatures and adequate oxygen supply. The tall flame zone ensured sufficient residence time for volatiles to burn completely. The concern about creosote buildup was valid, but top-down burning produces less creosote because volatiles burn more completely. Elias cleaned his chimney twice per year and found minimal buildup. The concern about fire going out prematurely was valid but rare in practice. As long as wood was dry and air supply was adequate, combustion proceeded reliably. In 2 winters of operation before 1888, Elias never experienced a premature burnout. The self-regulating nature of the system made it remarkably reliable. The concern about inability to adjust heat output was partially valid. With conventional stoves, you can add wood for more heat or let fire die down for less heat. With top-down burning, heat output is determined by the fuel load size and cannot be easily adjusted mid-burn. But Elias found this predictability to be an advantage rather than a limitation. He loaded the stove based on expected weather and cabin needs. The consistent burn rate provided stable temperatures without constant adjustment. The spread of Elias's design through Idaho territory was steady but not explosive. By 1890, approximately 40 upside-down stoves existed in the mining camps and settlements of the Sawtooth region. Each one provided superior performance to conventional stoves, but several factors limited wider adoption. First, construction required skill and precision. The vertical firebox had to be built carefully to ensure proper draft and stable fuel stacking. The air inlet had to be sized correctly. The exhaust heat exchanger had to be constructed properly. Not every builder had the skill or patience for this precision work. Second, the design was unconventional enough that many people remained uncomfortable with it. Fire burning downward just looked wrong, even when explained. Cultural resistance to unfamiliar designs limited adoption to people who valued efficiency over convention. Third, the design worked best with specific fuel. Split wood of relatively uniform size, stacked in neat layers. People who burned irregular wood, scrap lumber, or mixed fuels found conventional stoves more forgiving. Fourth, the initial fuel loading required some technique. Stacking 8 layers of wood properly took 10 to 15 minutes. Conventional stoves could be loaded casually in 2 minutes. Some people preferred the speed of conventional loading, even if it meant more frequent loading cycles. Elias himself continued using and refining his design through the 1890s. In 1892, he added a water heating coil to the exhaust heat exchanger, providing domestic hot water. In 1895, he experimented with adding thermal mass around the firebox, creating heat storage capacity that extended warmth after the fire burned out. These refinements made an already excellent system even better. By 1898, Elias had moved to Boise, where he worked as a consulting engineer for mining operations. He tried to interest manufacturers in producing upside-down stoves commercially, but found no interest. The market wanted cheap, simple cast-iron stoves that could be mass-produced. Custom-built, high-efficiency stoves were too expensive and complex for the mass market. Elias died in 1920 at age 68. His original upside-down stove in his Sawtooth cabin continued, functioning until the cabin was abandoned in the 1930s. Some of the stoves he built for others lasted even longer. There are reports of top-down stoves still operating in remote Idaho cabins as late as the 1950s, decades after Elias's death. But the knowledge of the design faded as people who understood it died or moved away. By the 1960s, the upside-down stove was a forgotten curiosity, a strange anomaly in heating history. Modern rediscovery of top-down burning came from an unlikely source: campers and outdoor enthusiasts. In the late 20th century, people experimenting with campfires discovered that if you built a fire with kindling on top of the fuel rather than underneath, the fire burned more cleanly and efficiently. This top-lit updraft, or TLUD technique, became popular in camping and survival communities. From there, engineers began studying the combustion dynamics and realized the efficiency advantages Elias had discovered a century earlier. Today, top-down fire starting is recommended by many wood stove manufacturers as the best way to start fires, even in conventional stoves. Some modern, high-efficiency stoves are designed specifically to promote top-down burning characteristics. Gasifier stoves, rocket stoves, and some masonry heaters incorporate elements of top-down combustion. But few modern stoves are pure top-down designs like Elias. Most are compromises that allow for some benefits of top-down burning while maintaining the convenience of conventional adding wood to active fires operation. The principle Elias demonstrated that combustion efficiency improves dramatically when burning proceeds from top to bottom through a fuel stack is now scientifically validated. Studies show top-down burning reduces particulate emissions by 50 to 70%, reduces creosote formation by 60 to 80%, and increases useful heat output by 40 to 60% compared to conventional bottom-up burning. These are exactly the advantages Elias observed in 1886. The practical lessons from Elias's work apply to modern heating challenges. First, combustion staging dramatically improves efficiency, separating drying, pyrolysis, and char burning into sequential stages, each optimized individually, extracts more energy than allowing all stages to proceed simultaneously. Modern gasification boilers use this principle. Pellet stoves use this principle. High-efficiency wood stoves use elements of it. Second, volatile combustion is where most energy resides. Ensuring complete burning of volatiles is critical. Modern stoves achieve this with secondary air injection and catalytic converters. Elias achieved it with geometry that forced volatiles through a high-temperature zone. Different methods, same principle. Third, preheating fuel improves efficiency and reduces emissions. Modern stoves are beginning to incorporate fuel preheating through heat exchange with exhaust gases. Elias did this in 1886 with his vertical stack design. Fourth, controlled combustion rate beats rapid combustion for efficiency. Burning wood slowly with adequate oxygen produces more useful heat than burning rapidly with excess air. Modern air-controlled stoves apply this principle. Elias applied it with his restricted air inlet. Fifth, exhaust heat recovery multiplies system efficiency. Capturing heat from exhaust before it escapes can double or triple useful heat output. Modern furnaces do this with heat exchangers. Elias did it with his jacketed exhaust pipe. The barrier to adopting pure top-down burning in modern contexts is primarily convenience. Modern consumers want heating systems that don't require attention or technique. Load and forget convenience. Top-down burning, at least in Elias's pure implementation, requires complete fuel loading at each cycle. You can't just add a log when you want more heat. You have to plan ahead, load appropriately, and let the system run its course. Many people find this constraining, even though the reduced tending requirement overall is a net benefit. Pellet stoves partially solve this by automating fuel feeding from a hopper, but they're burning pellets, not wood. The market for high-efficiency wood heating exists but is small. Modern EPA-certified wood stoves are significantly better than old designs, achieving 50 to 70% efficiency. But even these don't reach the performance Elias achieved. A true modern implementation of his design, using advanced materials and controls, could probably achieve 75 to 80% efficiency while maintaining safety and reliability. But the market demand isn't sufficient to justify commercial development. High-efficiency wood heating remains niche. The story of Elias Drummond and his upside-down stove is ultimately about questioning fundamental assumptions. Everyone knew fire burned from bottom to top. That's how fire works. Except it's not. Fire burns wherever there's fuel, oxygen, and heat. The direction is determined by where those three elements come together, which is determined by how you arrange the system. Elias questioned the assumption that fire had to burn upward. He designed a system where fire burned downward because that direction optimized efficiency. The result was a heating system far superior to anything his contemporaries built. His 52-degree temperature advantage during 12 below weather wasn't luck or exaggeration. It was the predictable result of applying combustion science correctly. Modern heating still has room for improvement. Residential heating accounts for roughly 30 to 40% of home energy use in cold climates. Even a 20% improvement in heating efficiency would be enormously valuable. The technology exists, the principles are known. The question is whether we're willing to question our assumptions about how heating systems should work and build differently. Elias was willing. His upside-down stove proved that different can be better. Before we wrap up, I want to ask you one more time, if you found value in this story, if you're thinking differently about efficiency and innovation, please subscribe to this channel right now. Hit that subscribe button, turn on notifications, join our community learning from historical innovations. Your support makes this work possible. Thank you. The winter of 1886 to 1887, when Elias first proved his upside-down stove in brutal conditions, should have changed how everyone heated their cabins. But it didn't. Most people continued building conventional stoves because they were familiar, because builders knew how to make them, because the fuel savings and comfort improvements of Elias's design weren't worth the effort of learning something new. This pattern repeats throughout history. Breakthrough innovations that threaten established practice face enormous inertia. People would rather suffer with familiar problems than risk unfamiliar solutions. Elias's upside-down stove suffered this fate. Recognized as superior by those who used it but rejected by the broader market as too unconventional. The knowledge persisted in small pockets, passed from builder to user, but never achieved mainstream adoption. Today, we face similar challenges. We know how to build homes that use 10% of the energy of typical homes. The technology exists, the techniques are proven. But we continue building conventionally because that's what we know, that's what codes specify, that's what buyers expect. Breaking this pattern requires people like Elias who are willing to question assumptions and build differently, even when everyone says it won't work. Thank you for watching this story about Elias Drummond and his remarkable upside-down stove. If this changed how you think about heating, efficiency, or innovation, please share it with someone who might benefit. And remember that sometimes upside down is actually right side up. Sometimes backwards is forward. Sometimes the thing everyone knows is impossible is exactly what we need to do. Elias's 52-degree advantage came from ignoring what everyone knew and following what physics required. Have the courage to do the same in your own challenges. Question assumptions. Follow principles. Build better. The upside-down stove that everyone said couldn't work kept one man 52 degrees warmer all winter. Maybe being upside down is exactly what we need.